Welcome to our session 6, Smart Systems for Sports Applications. I would like to welcome René Williams. He is Executive Director of the European Platform of Sports and Innovation, EPSI, and is the chairman of our session. Mr. Williams, would you like to introduce yourself?
Thank you, Evelyn. And I will put on my camera. If it's correct, you can all see me.
Yes, we do.
I would like to have the first slide because, yes, thank you. As said before, my name is René Williams. It's a little bit difficult, I understand it, but it's really the name. But thank you, Evelyn, for introducing me. First of all, welcome to this session on smart systems for sports application. I would like to say a few words to start with. As earlier mentioned this morning by my colleague Alberto Bichi, which with me is the co-executive director of EPSI, we are very happy to see this 2 days running around as being a link between EPSI and EPoSS. We are sure that this joint effort and event will help us to strengthen our connection further. Maybe it's good to know that besides being the executive director for EPSI, I'm also leading a cluster in the Netherlands, the south of the Netherlands. It's the cluster Sports and Technology, which is also on the slide. Sorry, we have some technical problems, so I have to ask for the slide change. Yes, thank you. It's a cluster in the south of the Netherlands, in the Brainport region, and this cluster is in fact a cluster that exists now for more than 15 years with 130 companies, SMEs, RTD organizations, living labs, and of course, clear link to the public sector. This is really a booming area for innovation for sports and vitality, and we are proud to say that we are in fact one of the oldest in this field, I think, in Europe. Having said this, we of course have also a lot of examples, and these examples, next slide please, are of course very much also linked to smart systems, because we are in a region where a lot of smart system development is taking place, and of course we are looking for applications in the area of business, but also social and health impact. So thus we create in fact innovative solutions that really help people to become active and to create business from. As Alberto Bichi, and maybe the next slide please as well, as Alberto Bichi already mentioned this morning, we are also being one of the 2 leaders of the Clustersport Smart Specialization Platform, which is in fact grouping together a network and cluster of regions throughout Europe that are all active on innovation and business creation for sports and vitality. They join their excellences and ambitions to create better business in sports and vitality and stimulate the healthy, active lifestyle. As you can see from this, we are in fact from both EPSI and Clustersport reaching out to organizations that are active in this field throughout Europe. So not only big companies, but also SMEs and startups in this field. In the previous sessions on smart systems for vitality, we have seen some nice examples for innovation for this area of sports and vitality. In this session, we will more particularly focus on the sports applications. Next slide, please. It may not be a surprise that there is a large overlap between the innovations for sports and the innovations for vitality. In general, we see a trend towards personalized products, personalized monitoring, and personalized services, not only for elite sportsmen or people that are already very active, but also for those that need to increase the level of activity. Personalization of products and services can be found in quite a number of applications, and I just have assembled here a few, like injury prevention, enhancement of performance, competing and comparison of performance, gamification, exergaming, nudging and of active behavior, stimulation of socializing, etc., etc. So there are quite a lot of I would say applications where personalization is important and smart systems come into place. In this sense, we see a strong link between elite sports, grassroots sports, and the topic of vitality. It is a pleasure to see that the different contribution in the coming session on sport is really contributing to that, and I would like to hand over the word to Evelyn to introduce the first speaker in this session. Thank you.
Thank you for this outlook, Mr. Williams. So let us come to our first presentation in this session with Anders Erik Lieverud. He is a senior research scientist at SynTef. Mr. Lieverud, you have the floor.
Okay, I just have to switch the screen here. Okay, can you see my screen now?
See your screen, and we don't see your webcam still.
Okay, I'll start the webcam as well. Okay,
Yes.
there we go. Okay, I'm going to talk about human motion tracking from heterogeneous sensor data. This is work done in 2 projects that we've done, and it's combined, so it's a sample of what we're doing. I'm from, by the way, from SINTEF, a department called Smart Sensor System that's located in Oslo. The first project, that this is a Excel project, the Silence, it's on ultrasound interfaces and low energy integrated sensors. And the second project I'm presenting from is a Norwegian research project called AutoActive. That's tools and method for analysis of human motion and wearable sensor data. Okay, so onto human motion tracking. The objective is for us is looking at analysis of gait. So a typical sensor system used for a portable sensor system is using lots of IMUs, that's inertial measurement units, that's measuring acceleration. It's a gyroscope for rotation and a magnetometer for direction. However, those suffer from measurement drift, and you need, if you have multiple of those, it's kind of difficult to know the exact position and so on for setting up a complete system. So what we have looked into in this project is to use ultrasound and then measurement of distance. So it's time of flight measurement. So we can actually measure the distance between such sensors on the body. So that is, the idea is then to measure where on the body these sensors are, and then to compensate for IMU drift. That is a common problem for IMU sensors. And then to make kind of a automatic body coordinate system. So we had looked at this in 2 use cases. In one is for the disease multiple sclerosis. There it's a typical test. There is a 25-foot walk test where you walk 25 foot and you just take time. We think that introducing IMU sensors and with a kind of system we're looking at with automatically deciding where on the body and the distance between these sensors, that could be a useful tool for this. Then that could help both patient and health personnel then just to confirm observations and quantify the effect of treatment. We also look at this into sport, then on high-level precision intercycle measurements for performance analysis, both for athletes and for coaches. So the common problem when using this kind of sensor-based measurement is that you have a lot of sensors providing different kind of sensor data that you collect, and you would like to combine all these for doing signal processing, dynamic models, machine learning, digital support, and so on, and analyze this with typical tools in Python and MATLAB. However, to prepare all these data, integrate all this data, is time consuming and not the most, well, it's demanding and not very useful. So what we looked at is to make a tool that is providing some interfaces to a few of these, or a plugin for interface for a few of these sensors, and then a software platform that you can take all these data, import it directly into this tool. It's called AutoActive Activity Presenter, where you can combine video from the performance or the data acquisition, and you can see the raw data. Then you can export all this data for data interpretation in Python or MATLAB, and then you can re-export or import the data again and get the results like you see up on the right-hand corner here. You can see the process data, video here so on the athlete, and then on the bottom here you can see the raw data. This tool can also then be used to synchronize all these different kind of data. So we added a synchronization module here with some helping tools that could ease that operation. So this tool is actually an open source tool that we will provide later this year. So back to this this prototype design we did with making a combination of IMUs and ultrasound sensors. So we made this prototype here that's got an ultrasound transmitter on the box there and a receiver that's a microphone. The transmitter is a as a PMUT transmuter, a MEMS sensor, or transmitter that's made at SINTEF MENA Lab. We got a department that's working on MEMS sensors. That's done this in the Silence project. And then we made the electronics and combined this into a fairly bulky demonstrator, but still it's operational. Then we did some characterization of this time-of-flight sensor, the combination of the transmitter and the microphone. And we see that it's got a wide lobe, so it could be used, and sufficient range as well to get this for our application. And then we did two kind of tests for this. It's treadmill walking, where we're walking for 5 minutes, measuring the length and the distance between these sensors. And we did outdoor walking that was simulating this 20-foot MS test that I showed in the beginning here. So we got the results here. We can see that this compares very well to the average. This is a dotted line. The ultrasound is the left one here, and the length of the steps from the IMU is on the right hand. And we see it matches very well for the two different test persons here, and the same on the outdoor. We get quite good results. On the blue line here, you can see the individual steps that's taken. So this is more on a dynamic base than the other measurements. So we can actually follow how this is going on throughout the walking. So I'm going to show a video now, short video demonstrating this system. And I'll see if I can find this one. There you go. So here you can see myself testing the system in the spring during the lockdown. So we had to do every test outdoors. First, we did some synchronization measurements that could be easy to synchronize the different sensors. Here you can see the walking. At the top here, you can see the distance between the sensors. And the second graph is the gyroscope and in the sensor module. And the bottom one is on a separate IMUs that's on at the shoes there. You also can see the movement there. So this is in the AutoActive platform that I talked about, this open source platform as well, showing this video. So if I now can move back to my presentation. Yeah. Okay. So what I have shown here, that is a combination of ultrasound motion tracking together with IMUs, that this can be done and can be a useful tool to improve this portable, low-cost motion tracking system. So it can be used to then get better position and angle estimates, both in the MS use case and within sport. So it's kind of a proof of concept, auto lab tested. What we will do further on is then to improve the accuracy of the system to a higher sampling rate, and probably also include multiple loudspeakers, microphones to increase the lobe for the system. And finally, to do a miniaturization, so this can be a small unit similar to what IMUs are today. This AutoActive activity presenter tool, that's a software tool that we made. It's portable and it's currently for Windows, but it will be possible to port to different platforms, and it will be made as an open source tool now available at GitHub now in Q4 this year. Okay, I think that completes my presentation.
Thank you very much for this interesting presentation, Mr. Lieberud. Our next speaker, Salvatore Tedesco, is Senior R&D Engineer and Team Leader at the Tyndall National Institute at the University College in Cork, Ireland. His presentation is about wearable motion sensors for the estimation of vertical ground reaction forces in running. Here you are, Mr. Tedesco.
Hi, everyone. Can you please let me know if you see the screen?
Yes, we can see it and we can hear it.
Hi, thanks very much. Thanks also for the introduction. I'm very glad to be here presenting my work. So the aim of the work was actually to design a wearable measurement system for extrapolating ground reaction forces during training. And the basic idea was to exploit the wearable sensors to extrapolate these ground reaction forces while running in order to support prevention programs against ground reaction, against running related injuries. So before starting the talk, I will talk a bit more about Tyndall National Institute, which is the biggest ICT research center in Ireland with particular interest in microsystems, micronanoelectronics, and photonics, etc. And also, Tyndall has been part of the EPoSS community for the last 10 years and has been a contributor to its strategic research agenda. In particular, I'm working in the wireless sensor network group, which focuses on developing low-power smart sensor system for a number of applications, with particular reference to healthcare and fitness. So, athletic performance, technique assessment, and injury prevention are all aspects of great importance nowadays for both coaches and athletes. And as a consequence, the new reliable performance monitoring and evaluation systems are seen as an essential tool by coaches and athletes to minimize the risk of injury. Therefore, wearable sensors represent an excellent alternative to gold standard lab-based assessment, such as optoelectronics or instrumented treadmill, because of very low cost and versatility. However, current technology in sport is not providing the key metrics to allow both coaches and the user to make training and performance related decisions in real time and in open field. So wearable may provide important insight into the kinetics responsible for injuries and support decision making processes by coaches. And also, ground reaction forces have been considered recently in literature as being associated to running-related injuries. Therefore, the aim of this work was to develop an IMU-based wearable solution which could be used by coaches and athletes in real-world practices to monitor performance and evaluate possible running-related injury risks. The system relies on 2 boards which are worn on the left and right shank of the runner, and they store data internally on their SD cards. A block diagram of the system is shown at the center of the picture, and it's seen that the 2 boards are wirelessly synchronized. And this is important in order to temporarily align the data that is being collected on the 2 SD cards. Finally, after running, the complex backend data analytics are used in order to extrapolate the various metrics of interest from the data collected on the SD cards. Moreover, a graphical user interface has been developed in order to visualize, export, and save the results of the analysis, and to allow coaches and athletes to easily interact with the system. For the project, we have developed a hardware platform which measures 50 by 90 by 10 millimeters and is equipped with a 32-bit microcontroller, 9 degrees of freedom motion sensor, Bluetooth transmitter, micro SD card for data storage, and a touch button for user interaction. And the achieved sampling rate here was 230 Hz with a battery lifetime over 4 hours. In this slide, I'm showing the flow chart related to the wireless synchronization between the 2 boards. I don't have enough time to go deeply into the technical details, but I can mention that the mechanism behind this is based on a three-way handshake between the 2 boards. Regarding the data processing, after the data collection, it is important to understand which are the part of the data which are related to running trials. For doing this in the algorithm, we rely on the sagittal axis of the angular rate, in particular, which is segmented into windows of 0.5 segments of length. Then the variance of the signal is measured for each window, and if it is above a predefined threshold, then that window is marked as active, otherwise it's marked as inactive. And finally, the algorithm considers all the consecutive active windows, and if that active sequence is above a predefined threshold, for example 20 seconds, then that sequence is considered as a running trial. And the picture here shows how the algorithm works. After that, we also developed a neural network in order to extrapolate the ground direction, the vertical component of the ground direction forces based on the acceleration collected from the data. So this was done using a neural network with 100 neurons in the input layer, a hidden layer of using TANH as an activation function, and then an output layer with 100 neuro again. The input of the neural network is based on the vertical component of the acceleration for each run instance, and the model was trained using a vertical ground reaction forces component using a ground truth as a validation purposes. Moreover, additional running metrics were also obtained, which are quite important for scientists, for example, contact swing, contact time, swing time, cadence, etc. Finally, as mentioned before, we also developed a graphical user interface, which was useful for visualization purposes and also to allow coaches and athletes to easily interact with the system. Some functionalities of the system involve loading the data from the SD cards, analyzing specific running trials, visualizing the results, exporting the results, and also formatting the SD cards directly on the SD card and on the hardware platform, etc. For testing, we recruited 14 healthy volunteers, which were asked to run on a treadmill at different speeds at 8, 10, and 12 kilometers per hour for approximately 30 seconds, using both the IMU developed for the project and pressure insoles for validation purposes. And you can see here the envelopes of the acceleration and the ground direction forces collected during the trials. For testing, so the results here we can see are actually the predicted ground direction forces in orange and the actual ground direction forces in blue, which are both body weight normalized at different speeds. And you can see actually that the neural network was actually quite accurate with low error, root mean square error, which was quite low and quite uniform at the different speeds, and the average was around 0.13 body weight. And also this one was quite a good improvement over the state of the art, because for example in literature you see that other papers using motion sensors on the lower legs and the pelvis adopted a neural network to extrapolate the vertical ground direction forces with a root mean square error of 0.27. So it was a good improvement over the state of the art. So in conclusion, for the project, we have developed a novel wearable IMU-based system for athletic performance assessment during running, and the system was also tested with satisfying outcomes. And it could be also extended to evaluate the jumping-related tasks and other activities, which is something we are working on currently at the moment. In the future, the system could be adopted as a performance evaluation tool to support coaches and athletes in real-world practice, and also we are looking for a large-scale deployment opportunities, which could potentially lead to the widespread measurement of biomechanical loads in overfield. And moreover, we are also looking at targeted calls at the European level to push the project forward, and I will talk a bit more about this during the brokerage event later on. With this, I would like to conclude the presentation. I would like to thank our funding bodies who supported the research, and in particular, I would like to thank Setanta College, which is an Irish SME who focuses on sport and strength and conditioning, and who collaborated with the project, and with which we are in the process of licensing the current technology. Also, I would like to thank you for your attention, and if you have any questions, just feel free to ask at the end of the session, or to drop me an email, or to contact me later on at the brokerage event. Thanks very much.
Thank you, Mr. Tedesco. We come now from running to cycling. Our next speaker, Peter Bowens, is a researcher at the Ghent University and will talk about a standalone motion tracking suite for optimizing cyclobiomechanics. Please, Mr. Bowens.
So I hope you can hear me and see my screen for now.
Both very well.
All right. So good afternoon, everybody. So in the next 10 minutes, I will talk about our progress in our standalone motion tracking suite that we're developing. In this case here for cycling biomechanics, it's actually a collaboration between two groups. You have the engineering side, so I'm part of CMST, which is a lab from Ghent University and an affiliated lab from IMEC, together with more clinical side, the rehabilitation sciences, also from Ghent University. So why would we need a suit like this? So I'm from Belgium. Cycling is in our blood. We have produced a lot of very famous professional cyclists. And if you look on our rows, you also see a whole lot of amateur cyclists. And these, yeah, they spend a lot of time and money in their hobby. They're buying very expensive gears, expensive bikes. And with this also follows a bike fitting in a lab where the bike measurements are adjusted to be optimized for aerodynamics and also maximum power output, which results in a traditional bent back that you see here. This by itself is already not that optimal, but the real problem comes when you're driving a couple of hours and you're getting tired, then you're unable to hold that position. And yeah, you're going to compensate. And then, yeah, this compensation is not always good. You're going to shift in your saddle. In the medical terms, they say that the pelvical anteversion is lost, which means that the rotation of your hips is not optimal. And then you're going to compensate by shifting in your saddle, having excessive movements of your hips, which might cause problems. For a professional, this doesn't have to be a problem because they are aware of that. They know how to compensate properly. They also have more strength, a more core strength, so they will be able to compensate for that properly. However, in the amateur side, often they ride their bike once a week. They have a less than athletic body. They lack the core strength, so they might really be prone to injury because of this compensation. So this is one of the investigation topics of the medical side. So what they do is they put a person on a bike, they cover him with infrared markers, and they just make him tired on a bike. So you can see here that he's covered with markers. There's a very expensive camera system that follows these markers to see how he is coping with this compensation. The problem is that you can see it's not really accessible for recreational cyclists. It's expensive. You have to go to a lab. And on top of that, it's not a real situation. There is a big difference between riding your bike on a roll in a lab versus going outside, riding on cobblestones or tackling a steep incline or something like that. So what we want to do is basically having the same measurement, but then by having sensors integrated into the suit itself. So the person can just put on a suit and go outside and ride his bike, and we can have the same measurement. So it should be hopefully cheaper than this camera system, and you can just use it everywhere. And our goal is then to have an injury prevention for the recreational cyclists, and perhaps also some performance enhancing for the professional cyclists. So how do we do it? So we focus mainly on the lower back and the movement of the hips. And we do this by using inertial movement units, IMUs, and as opposed to the absolute 3D tracking that you have with the motion capturing solution. This will just follow the orientation of the sensor, but with some data analysis, we can get similar results actually. So in our case, we use 5 sensors, 3 that will follow the spine curvature and 2 that will be placed on the hips for the pelvical movement. And right now we have a data resolution of 50 Hertz, but that can be increased if necessary. So quickly, some things on the hardware. So you have the IMUs that you see over here. They are placed on a very small board that is also quite thin to make it a little bit flexible. They are all connected to each other, and then they come together in a master controller where the controller is that will actually perform the communication, so it's an I2C communication. Then we also have an Bluetooth module that will then capture the data from the microcontroller and just send it away. So what do we actually want? We want just a suit with this integrated sensor system. So first of all, the sensors or the sensor system itself needs to be very flexible and stretchable as to not impede with the movement of the cyclist, of course. That's one thing. And secondly, of course, it needs to be very robust because you're going to have to use it a lot and you're going to move a lot. And ideally, if you're going to ride your bike for a couple of hours, you're going to sweat, and we want it to be washable as well, of course. So I will quickly go through the integration part itself. So we start, it's actually a quite basic system to start with. We start with just a copper on polyimide foil, where we, using standard lithography, we etch the copper tracks. So inside one meander, there are 4 tracks, so 2 for the SAC communication and 2 for ground and supply. We put on some overlay and we laser everything out. So in the end, we get a very flexible and stretchable connection system with pads that we can then use to solder our boards on. So that's what you can see here on this picture. The sensor boards are soldered onto the circuit. These will be laminated into the textile. What cannot be laminated for now is actually the master control itself, because I have larger components there. So here we just have an interposer. And this whole thing we laminate with TPU on a piece of textile that is very similar to the textile that is used in the cycling suit. And we, of course, leave a hole here where we can afterwards then put the master controller. And then this whole thing is again laminated with TPU and laminated onto the suit itself. So you can see it here. Then we can still cut some things away to actually make it even more flexible. But you see here that the sensor boards are actually completely laminated or integrated between the textiles, so normally quite sturdy. And they follow the positions where they need to be. And then lastly, we solder the master controller board together with the battery. But I will come back to that in a moment. So then on the software side, like I said, everything is sent through Bluetooth, which means that any Bluetooth capable device will be able to capture this device. This can be either a smartphone or a custom device on the bike. In our case, this was a laptop. And on this laptop, we have a Python script running that has a 3D visualization of the posture of the cyclist. So what you see here, these red dots are actually representations of the sensors itself, and they are connected to a black bone, let's say, and then these bones are connected through joints. So if you have the orientation of a sensor and you map it to the respective orientation of one of the sensors over here, you can actually have a quite correct 3D visualization of the person on the bike. But it is just one thing you can do. What you see here below, for example, is actually the 2D angle between 2 of these sensors. For example, 2 sensors on the spine, and then this can then give an indication of the curvature of the spine. Normally, there's also a video that can be shown here, so I would ask the moderators to start the video. What you see here is actually the person wearing the bike, wearing the shirt. And then you can see here on my laptop screen the 3D visualization and the slight movements of while he's riding on his bike. So that shows that it's working. I will try to re-share my screen now. Is it visible? Okay. So that shows that it's working. Of course, there are still a lot of things that needs to be done. I was talking about robustness and washing tests. These are actually 2 of the most important things that we are still investigating. So right now it's working, but it's still quite fragile. It works for, I don't know, a couple of hours, but because of the putting on and putting off and a lot of movements, things start to break, especially if you're looking at washing tests. The suit needs to be very robust to be able to be washed, of course. So this is something that we're working on now, seeing how to improve our stack that they actually survive these washing tests. Another thing, if you want to be able to wash it, the master control is now just soldered onto the suit itself. you can clearly see that it will never be washable like this. So we're working on some systems to easily attach and detach this master controller. Also, it will make it a lot easier to charge the suit, because now we have to put the whole suit and charge it at your laptop, for example. And last but not least, the software. What we did now is very basic, just a 3D visualization, but you can do also a lot more with that as well, of course. Then I will come to my conclusion. So I showed you the first version of such a tracking suit, and it's shown to be functional. The posture can be visualized. You can store all the data. It can be used afterwards for further analysis. And our hope is to reduce the injuries in recreational cyclists. And with that, I think my 10 minutes are on. So I would like to thank you for your attention. And if you have questions, I will be glad to answer them at the end of the session. Thank you.
Thank you, Mr. Wowens, for this interesting insight. We are now looking forward to the presentation from Jérôme Boutet. He's a researcher at the French Technology Research Institute CELATI and will talk about classifying boxing strikes by artificial neural network embedded in a wristband. We are curious for your speech.
Good morning, good afternoon, everyone. Do you see my screen?
We see you, we hear you, and we see your screen.
Perfect. So I'm researcher at the Laboratoire Système et Signaux de Capteurs from the French Atomic Energy Commission. This is a laboratory specialized in signal analysis and machine learning applied to human activity and emotion recognition. By the end of the talk, you will know how to classify boxing punches by the means of a simple and shallow neural network. So first, the problem of human activity recognition has been widely studied in the past. It's generally tackled by the use of inertial measurement unit and or with 2D or 3D video sensors. The segmentation of the punches or of the activity may be done by the use of fixed windows, event-based segmentation, or adaptable window with machine learning algorithm. The classification is made by using features extracted from time frequency analysis, and the classification can be done by hidden Markov models, dynamic time warping, random forests, supervector machines, and neural network. And all of this requires a very nice, properly labeled database. And in particular, even if there are plenty of publications about human activity recognition, the field of combat sport analysis is under research, under 3% compared to their adoption by the population. On the scientific point of view, it's a difficult problem to deal with as there is a wide range of accelerations. The punch's duration varies highly between the level of practice, and finally, there are no idle periods between punches that we may be used to detect the start and the end of a new punch. However, one can find some studies on this particular topic. These mainly try to assess the performances of athletes in the field of strike quality, classification, sensor and method used require the use of accelerometers. Half of them use a gyrometer, and very few use the magnetometer. The methods are generally classification trees, CNN, KNN, and so on. The results show an accuracy between 96 to 99% of accuracy, depending on the number of classes and the side, right or left hand. But all of these previous works require a period of idle period of 10 seconds between each strike to allow proper recognition of the class of punch. So the aim of this study was to develop a new segmentation method for consecutive punches analysis. And this method had to be associated with a feature set and a classification method adapted for 3 classes of boxing punches for the 2 sides, so a total of 6 classes. All of this has to be embedded as a real-time analysis tool on a low resource platform placed on the wrist of the boxer. So let's talk briefly about the hardware platform. The microcontroller unit relies on an NRF52 system on chip from Nordic, which contains an ARM Cortex-M4 CPU with floating point unit running at 64 MHz and supporting Bluetooth Low Energy. To this, we added one high dynamic range accelerometer and one inertial measurement unit from Bosch. We also added an inductive charging unit, and all these elements are placed on the left and right wrists of the boxer, and it's everything is held firmly with a wristband. So, in order to train the model and assess its performances, we contacted a French boxing club of Ivry-sur-Seine, and we performed analysis on 10 subjects of various level of experience in boxing. And so the size of the database is about 1,500 strikes, punches. So I will not dwell further into the detail of the protocol and jump right into the core of my presentation, that is to say the signals. On the right, you can find the accelerometer signals in 3D for one punch, one typical punch. It's a jab. So the first part of this signal corresponds to the arming of the punch. The second part, which is a negative peak, is the acceleration of the peak, and the larger peak, the largest peak, it's a positive one that you can see, corresponds to the end of the punch, the maximum extension of the punch. So this is a punch performed in the air, but we also performed punches on a target, on a practice target. And in this case, this second punch, this second peak is way higher. And the last peak that you can see, it's again a negative peak, corresponds to the return of the punch of the wrist and the end of the movement. On the right, you can see a sequence of 10 jabs, and sometimes it's very difficult to separate the end of one punch to the beginning of the next one, and that's why we developed a specialized segmentation method dedicated to this problem. This segmentation is based on a state machine with no less than 8 states to take into account different ways of performing strikes. And the particularity of this state machine is that it was studied to ignore feints and footwork of the boxer. Because before we tried to do it without a state machine, and we had a lot of false strikes corresponding to feints that we do not want to take into account. So I will not dwell further into detail on this state machine, but if you want to have more information, you will have an article that will be published in the next month about this topic. So classification. The features are extracted in real time and composed of maximum, minimum, and standard deviation computed on the 3 axes of the accelerometer and gyrometer. We also used a feature extracted from the speed and amplitude after integration of the acceleration in the mobile frame. That led us to more than 30 features, which were fed into a neural network for classification. This network is very simple. It's composed of the 2 layers, one fully connected hidden layer and one output layer, providing the estimate class of the punch. To assess the performances of the classifier, we performed a tenfold cross-validation with the following pipeline. On each fold, optimization of the hyperparameters on the trait test, and then test on a dedicated test set of measurements. We also analyzed the feature importances after having removed the features correlated above 95%. And this is a box plot of the 2 main features. And as you can see, one feature alone is not enough to separate the different kind of strikes. So this validated our approach to use a machine learning approach to combine all these features to perform a decision. Finally, the results. As the database was composed of a balanced number of classes, we used the accuracy as our performance criteria. When performing tenfold cross-validation on the database, we obtain 96% of global accuracy. Error comes mainly of confusions between jab and hooks. To estimate the performances of the pipeline on a new subject, we also performed a leave one subject out validation, making the accuracy drop to 88%. And in this case, misclassification errors mainly come from beginners with poor techniques or short punch amplitude. As a conclusion, we developed a segmentation method dedicated to the detection of the start and the stop of the punches in a sequence. And the main caveat concerns the slow or low intensity movements that are sometimes not detected. The classification by a shallow neural network works pretty well, between 80 to 96 of accuracy, depending on the cross-validation method. And as a follow-up program, the system was installed in several fitness rooms by the startup MoveLab to add a gaming experience to physical workouts in the way of an immersive simulation where you have to destroy asteroids threatening a spaceship by performing punches. And that concludes my talk for today. If you have any question, feel free to ask them in the next session.
Thank you, Mr. Haake. As you just said, I would just now like to hand over to Mr. Violence to start the questions and answer session, and ask all speakers of the session to turn on their cameras, please.
Yes, thank you, Evelyn, and thanks to all the speakers also for their excellent presentations. I really liked it. It's nice to see how things are covered in a similar way, but from also different sides. And I think there's some mutuality in between the different contributions. So that's interesting, maybe also to discuss among yourselves a little bit. But before we do that, we would like to discuss some of the questions that came up. First of all, there's a question, I think, to at least the first 2 presenters from, in fact, the idea of how are we going to achieve the market in the end. So there's, of course, there's a clear market, but there's also a gap. And how do you see this gap being solved? Anders, Eric, can I ask you this first?
Okay, yeah. This is a kind of a low TRL, relatively low TRL level project at the moment. We're about level 5 or 6, you could say. So it's fairly far from market here. One opportunity is, of course, to go. There are some IMU suppliers commercially available, so we could cooperate with some of those to make this product. That's an opportunity. But I think first we would like to test this a bit further ourselves and see if we can, get the next generation done and see if that can be even be made more proper and get better data from that than the current version. So there is a yeah.
Yeah, thank you. I'll come back maybe on this topic later on. Maybe Salvatore, for you the same question. How do you see this trajectory towards the market?
Well, the answer is very similar to Andres Eric. So Tyndall doesn't develop product but prototypes for research. So at the moment we are around the TRL 5.6. So what we are looking for, and I mentioned that in the presentation for the brokerage event, is actually partners for commercialization, or something that we are looking for is to transfer then the technology that we developed. And I think that there is an opportunity here. There is the market in the running space is actually full of devices at the moment, especially for the consumer market. And also another opportunity is the fact that regarding the project that I'm presenting, we are using a more, let's say, scientific approach compared to other devices that are already here, are already there on the market in the running space. For example, now there are a number of devices of companies, I don't want to mention the name, but they provide something that is indicated, for example, like impact score, biomechanical load, bone load, and you can see that actually you don't know how scientifically this metric has been estimated, evaluated. So in the best case scenario, this is actually confusing or misleading for the person, for the consumer using the device. But in the worst case, can be even harmful because you don't know the biofeedback suggested to the runner, how has been obtained and calculated. So actually, we prefer to have this more scientific approach where we extrapolate the full ground direction force waveform, and we extrapolate the metrics from there, and we just say, this is the way we do it. This is scientifically validated. So also the biofeedback that you get from that will be scientifically validated.
Thank you. Indeed, you have put forward also to the brokerage event this question of finding access to other partners as well, and I think that's a fair thought about this. If you look at the two topics that you are both addressing, Anders and Salvatore, you are all fixed also to the human being, of course, in one way or the other. How is this fixture going to work from, well, the bulkiness or the linking to the body, so actually as to be able to get the right signals going on? Is there any thought about that? Salvatore, maybe you first, or?
Actually, so can you repeat the question? I'm sorry.
Oh, sorry. Well, I'll try to rephrase it a little bit. So if you have a sensor on a subject, of course, it is linked to the subject. And of course, there's always a difference between what the subject is doing and what the sensor is saying. Of course, this counts for every one of you, actually. This is always the challenge in how to do that in biomechanics. And the question was how you manage that and how you are sure that you are having the right standard here.
Well, let's say one of the approaches that we could follow on this is the development of personalized models in terms of machine learning and the neural networks that have been developed. So this the model that has been developed with the neural network is, let's say, is person independent. So it's trained using a number of subjects, but also one of the other approach is to have even a better outcomes for a specific person is to train the model using the data specifically for that person. And so in that way, we can get a biomechanical model which is more accurate and more precise, personalized for each runner. But that involves that we need hundreds of runners and lots of data to collect to achieve that point.
Okay.
I hope that question.
Thank you, Salvatore. Anders, do you have an addition to this?
Seems reasonable. What we got today in these use cases I talked about, the MS and sport, it's usually today it's just visual inspection, and it's that's not very accurate. So I think everything that you can measure and actually record is a big step forward.
Okay.
So yeah.
It's a step-by-step approach, as I understand. Peter, do you want to react? Because for you, it's of course it's a similar situation. A subject measuring and getting data from this? You're muted.
Yes, I think, and that is one of the things that we want to approach by really integrating the sensors into the suit itself to make it more close to the body and as light as possible, so that what is measured is actually closer to the real situation, let's say, than a sensor that is further removed from the body. So that is one of the ideas that we want to do to integrate it into the suit itself.
Thank you. Another question related to the materials you are using is about the washable conditions of that. Can you explain a little bit on that? And maybe to start with.
Yeah, I assume that you mean how to make it washable. So the materials itself are washable?
Well, in fact, a combination of what materials do you use for the sensor laminate on the shirt, and how is that related to the washing conditions?
Okay, so right now it's just like I have shown in the presentations. There's 2 pieces of textile with TPU and then laminated together. But it's actually, for example, one basic thing that you can change is really the thickness of the TPU. So if you have thicker you make it, how more robust it will be, how less permeable it will be for the water. So it's the materials itself. And then also, for example, the setup of the stretchable circuit. There are some points that are very crucial. For example, the soldering joints, or where you go from a flexible material to a more rigid material. These are very sensitive points. And you could change the structure of, for example, your flexible part to have a little bit more reinforcements on these things. But it's always the same thing. You try something and then you put it in a washing machine and then you see how it comes out and then you try to readjust. So it's a quite reiterative process.
Thank you. Related to the presentation of Jerome, I already saw that you had a very good linkage to an application actually, which is in the gaming industry. But have you also looked at other applications, for example, for jury purposes? In Taekwondo, for example, that's a big issue.
Sorry, I did not get the question.
Well, your application for, in fact, scoring is in fact related to an application now in, for example, gamification. But also for jury sports, it's interesting to see how this could evolve. Are you working on that, and what is the perspective in that direction?
We try to design an approach that is more as modular as possible. And on the machine learning point of view, we are working on incremental learning. That is the possibility to add new classes to an existing algorithm. There are several methods that one can use to perform this. You can add a new part to the network and make the network learn on new acquisitions on a totally different subject that the training set. To add classes, to add new features to the classification, and yes, we are currently working on this topic.
Okay, thank you. Well, because of time reasons, obviously Evelyn is here again, so that's a good reason to stop our discussions. Thank you to all the speakers for your interesting contribution. I will see some of you in the brokerage event later on. And thank you for this time, and hope to see you further. Evelyn, the words to you.
Thank you all very much. Thank you for the questions and for the answers to all the panelists, and for Renew-Islands for the chairs or chairperson. Before we, as mentioned, there will be a brokerage, and now Alberto Bichi will say a few words on this. Alberto, please switch on your mic. Unfortunately, we can't hear you. We see you well, but we don't hear you. Okay, I think yes.
Well, I could do it, maybe. Alberto?
Yes, that would be perfect.
Can you hear me? Can you hear me now?
Just back again.
Now we hear you. Thank you both.
You can take it over, no worries.
Okay, sorry about that. There was a bit of confusion, not real what happened, not sure what happened. Anyway, just to let you know that indeed, as I was mentioning this morning, we would like to be as concrete and as practical as possible. And so we have decided to organize together with René and also EPSI project manager, Carlotta Giussani, 3 workout brokerage sessions, and these 3 broken session will be on smart system to overcome COVID-19, smart system for sports and vitality, and smart system for sports application. So as mentioned, we have a number of pitches that will be presented during these brokerage sessions. And you will see here on the screen the 3 GoToMeeting links that you will have to link on depending on the brokerage session that you have opted for. And indeed, so what is the objective? The objective is very much to enter into the nitty-gritty, into interaction, conversations between participants and speakers. And so there will be a number of very clear questions on why did you select this, for instance, breakout session. This is for the participants. Following the presentations from the different pitch presenters, we will also ask, what can you bring as added value to the pitch presenters, for instance, and so on and so forth. So I guess that this is, it's a bit unfortunate that we are not, as I told you before, in physical form, because when we are in physical form, the interaction works much better, but we'll try to do our best to make sure that ultimately there will be an added value for all the participants and also the presenters. Evelyn, I think that this is as much as I wanted to say about the brokerage. Please come along. Everything starts at 3 p.m. And please select one of the 3 links hereafter for the brokerage session you would like to attend to. Thank you very much, Evelyn.
Thank you, Alberto, very much for this preview. Yes, as mentioned, the brokerage will take place in 3 parallel sessions, and you have received the links by mail, and you can also find them in the chat box. Well, this was a very intense day, just like yesterday, and filled with interesting presentations, questions, insights. And now it's time for me to say goodbye and to thank all the speakers, the chairpersons, and all participants for great 2 days and a successful annual forum 2020. I wish you a stimulating exchange during the EPoSS brokerage after the 20-minute break, and the brokerage will start at 15 o'clock. Many thanks and goodbye.